Okay, welcome. We have 3.5 graphing techniques, which is basically transformations, right? No baby today. Okay, cool. Okay, so we will be transforming functions, so it's very important to know what the parent function is and what transformation we are applying. So the first transformation is a vertical translation, which means that if a number k is added or subtracted to the outside of a function, then we will shift the graph up k units or down k units, as stated there in the orange, right? So that is a vertical shift. It's pretty straightforward. Plus k, you go up k, minus k, you go down k. Okay, horizontal translations. Here's where it gets tricky. Whenever you handle a horizontal transformation, you always have to think opposite. Always think opposite. So for the first one, we have if a number h is, we say, added or subtracted to the output of the function. So if it's f of x minus h, this means we will shift the graph to the right h units. So x minus h means we shift to the right. If it's x plus h, then we shift to the left h units. That's why I say for any type of horizontal transformation, you always think opposite. So x minus h means move everything to the right. X plus h means shift everything to the left h units. So a little different than vertical. Vertical is straightforward. If it's plus k, you go up k. If it's minus k, you go down k. Horizontal, x minus h means you go to the right. X plus h means you go to the left. So horizontals are the only ones you think opposite on. All right. With that being said, let's go ahead and practice these new transformations on the given parent functions. And a parent function is a function before any transformations have been applied. That's what a parent function is. So x squared, square root of x, absolute value of x, anything without a transformation. All right. So we want to graph x squared, the parent function, and then we want to graph it with the applied transformations, x squared plus 3 and x plus 3 squared. All right, so let's see what those look like. So once again, it's just easy to make XY charts for all of them. We will start with x squared. Where can I put it? Right here, I guess. Keep it level. So for f of x equals x squared, my XY chart. I'm gonna pick, I want some information. So let's go from -3 to 3. -3, -2, -1, 0, 1, 2, 3. Plug all those into x squared and we'll get 9, 4, 1, 0, 1, 4, 9. Okay. And then I guess we can go ahead and plot. All right. So for x squared, 0, 0, 1, 1, 2, 4, 3, 9. Same thing, -1, 1, -2, 4, -3, 9. And connect. So here is the parent function, x squared. Now let's graph the first transformation, x squared plus 3. where it's important to make note of what type of transformation we have here. So the plus 3 is a vertical shift up 3 units. A vertical shift up 3 units. Okay, so to do these transformations, we are going to pick the same x values that you see on the parent function. Because since this is a vertical shift, the x values don't change, only the y values change. Any type of vertical transformation only affects y values. So my x values will stay the same. So -3, -2, -1, 0, 1, 2, 3. Okay, and then to account for the vertical shift up, well, we're going to take all the y values from the parent function and add 3 to them. That's all we're doing here. So take all of these values and add 3. That's what we're doing. So I'll get 12, 7, 4, 3, 4, 7, 12. And that's how the transformation works. You just take the parent function, you take the y values from this parent function, and you add 3 to all of them, and you'll get these new values. All right. How do you know that you're doing it right? Well, test the number. Let's test 0, 3. If I plug it into the function above, if I said f of 0, we would get 0 squared plus 3, which would give me 3, which means that point checks out. And that means all the other points will check out. So it's important to check. All right. Now let's graph the vertical transformation. All right. -312 is not going to fit, but -27 will. -2 and 4, 5, 6, 7. And then -1, 4. 1, 2, 3, 4. That fits. And then 0, 3. 4, 7. And here is our vertical transformation when we shifted the original graph up 3 units. And just connect. Maybe better doing different colors, right? Let's do it with red again. And you see all the x values from the original function have been shifted up 3 units. Here was 0, 0. We shift up 3 to 0, 3. And the same can be said for all the other points. So there's our vertical transformation. Now we want our horizontal transformation. X plus 3 squared. Okay. And once again, very important to note what transformation we are given. This is x plus 3. So this is a horizontal shift left 3 units. So we will take all the x values now from the parent function and shift them left 3 units. So let me make my little XY chart. Oh yeah, and when I make my XY chart, since we're taking the x values from the parent function and shifting them left 3, this means we are subtracting 3 from all the parent function's x values. So my xy chart should look like this. And since it's a horizontal shift, it only affects the x values, so my y values will stay the same. So now, all we have to do is take all of these x values from the parent function and subtract 3 from all of them. So if we do that, I'll get -6, -5, -4, -3. Nope, running out of room. So we have -3 and then -2, -1, and 0. And since the y values are unaffected, all we have to do is take these y values and just copy and paste them right there. So 9, 4, 1, 0, 1, 4, 9. And once again, check your work. Make sure we're on the right track. Let's check the point for -1 or -4, 1. Plug that into that function, and you'll have h of -4 equal to -4 plus 3 squared, which will give me -1 squared, which gives me 1. Which makes the point true that when x is -4, y is 1. So that point checks out. All right, all we have to do now is graph the horizontal shift. So -6, 1, 2, 3, 6, and 9, there's that. -5 and 4, there's that. -4 and 1 right there. -3, 0. -2, 1. -1, 4. Hey, that shares a point. 1, 2, 3, 4. And 0, 9. There we go. Graph that. And those are shifts up, down, left, and right. So you see from the original x squared function, we have in the red, we have vertically shifted it up 3. And then the green is just taking it and shifting it to the left 3 units. So these are all the transformations for vertical and horizontal shifts. That's how they work. Okay, now let's get into the other transformations. The next ones we get into are stretches. So once again, vertical stretches are pretty straightforward. If the right side of a function is multiplied by a positive number a, then the graph is vertically stretched as long as a is greater than 1. So if I had y equals 2x, the graph of x would be stretched by 2. You would multiply all the y values by 2, which means you stretch those y values. That's what that means. So once again, vertical stretches, straightforward. Whatever number's in front, you'll multiply all the y values by that number and stretch them. Now, a horizontal stretch. Here's where we think opposite again. So When the inside of a function is multiplied by a positive number a, the graph of the function f of a of x is obtained by multiplying each coordinate on the graph of f of x by the reciprocal of a. So if the number inside the function is between 0 and 1, then you will multiply all the x values by the reciprocal of that number, meaning you will horizontally stretch all those numbers. And this is why I say for horizontal transformations, you always think opposite. So if you look at the first example, this is a horizontal stretch. Yes, the number inside is 1/2, but since you always think opposite, you are going to multiply all your x values by the reciprocal of 1/2, which is 2. And that will stretch all your x values. So once again, horizontal, any type of horizontal transformation, always think opposite. All right. Whew. So let's try these two out. So we are given the parent function the square root of x. Let's graph the square root of x, the parent function, and then graph the transformations given above. So first up, let's graph the square root of x. So f of x is the square root of x. So my xy chart. Let's pick some numbers for the square root. And this one should be simple because we know we can only choose perfect squares greater than or equal to 0. So we start with 0, 1, 4, 9. That's all we're going to need. Square root of 0 is 0, 1, 1, 4, 2, 3, 9. So let's graph the square root of x. Zero, 0, 1, 1, 4, 2, 9, 3. There's the square root of x. Okay. Now let's graph the first transformation given. G of x equals to square root of x. And remember, it's important to note what type of transformation we're using. So this 2 in front is going to be a vertical stretch, which means we will take all the y values from the parent function and multiply them by 2. Because remember, any type of vertical transformation only affects y values. Okay, so let's take the xy chart from the parent function. The x values stay the same, but now you're going to take the y values, all these y values, and multiply them by 2. So 0, 1, 4, 9. And now multiply all the y values of the parent function by 2. 0, 2, 4, 6. There you go. Once again, check your work. Take 4, 4, plug it into the function above. G of 4 is equal to 2 square root of 4, which gives me 2 times 2, which gives me 4. 4, 4. Checks out. So we are on the right track. Okay, now let's graph the vertical stretch. Zero, 0, 1, 2, 4, 4, and 9/6. And here is the vertical stretch, the vertical transformation of the square root of x. There is 2 square root x. We have just taken all those y values, multiplied them by 2, stretched them by 2, right? So, all right. And the next transformation is the square root of 1/2 x. All right, so what we notice is that this number, 1/2, is between 0 and 1, just like the definition states, right? 0 less than a less than 1. So this 1/2 is less than 1, meaning that this is going to be a horizontal stretch. So you get a horizontal stretch by 2 units, right? You multiply all the x's by 2. So a horizontal stretch. All right. XY chart. Before I put that. So now, since it's a horizontal stretch, and remember you always think of horizontal transformations being opposite, so we're not going to multiply our x values by 1/2. We have to multiply all the x values by the reciprocal of 1/2, which is going to be by 2. So we'll have 2 times x, and the y values from the parent function will stay the same. So what we do now is take all these x values from the parent function and multiply them by 2. You get 0, 2, 8, 18. And your y values are going to stay exactly the same. 0, 1, 2, 3. And once again, I'll say it and I'll say it again. Check your work. Let's try 8, 2. H of 8 gives me the square root of 1/2 times 8, which gives me the square root of 4, which gives me 2. So we get 8, 2 as our point, which checks out right there. Okay. Let's graph. 0, 0. Share that point with all of them. 2, 1. 8, 2. And somewhere out there is 18, 3. And there is 1/2 x. So you have just taken your x values and stretched them by a multiple of 2. All right, why is the screen? I just noticed the screen's like this. There we go. Better. Okay. All right, so right now we have learned vertical and horizontal shifts, and now we just learned vertical stretches and horizontal stretches. All right. And just remember that for all of these, we have just been transforming the parent function. That's it. Okay. All right. So next is compressions. So we have, okay. So a vertical compression now says that if the number multiplied to the outside of a function, given a times f of x, if this number is between 0 and 1, right? If this number is between 0 and 1, then it will be a vertical compression, right? It'll be a vertical compression. Pretty straightforward. So if the number out front was, let's say, had f of x equaled 1/3 x, you would take 1/3 and multiply all your y values by 1/3. Once again, vertical compressions are straightforward. A horizontal compression, always think opposite. Now, once again, if a number is multiplied inside the new function giving us f of a of x, well then no matter what, we will always multiply by the reciprocal. So no matter what number is inside the function, you always multiply by the reciprocal. And if the number is greater than 1, this means this will now be a horizontal compression. So I guess one thing to take away is whatever number is inside that function, just multiply by the reciprocal. That's it. Okay, that's vertical compression, horizontal compression. Now let's try these out on the given parent function, which we are given here the absolute value of x. All right. I mean, maybe I don't need to zoom in. Let's see. F of x is the absolute value of x. Let's make our xy chart. And I'm going to go from, let's just do -2 to 2. Let's see what happens. -2, -1, 0, 1, 2. Perfect. Plug those into the absolute value, and you'll get 2, 1, 0, 1, 2. All right. Plot that. -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. And this function would go straight up this way. Straight up that way. So there's the absolute value of x. There's the parent function. Now, we get g of x is equal to 1/2 x. So let's try that out. One half absolute value of x. Once again, make note of the transformation. This is a vertical compression. So this means you'll take all the y values from the parent function and compress them by multiplying by 1/2. Which means when I make my xy chart, I'll have x and 1/2 times y. X values stay the same. -2, -1, 0, 1, 2. Y values 1, 1/2, 0, 1/2, 1. Okay. And plot the vertical compression. So -2, 1, -1, 1/2, 0, 0, 1, 1/2, 2, 1. And draw. You can't get that one straight. There we go. And there is 1/2 absolute value of x. All right. And you know, yes, you could check your work by plugging your points in. Okay. So last one is h of x equals the absolute value of 2x. And now, since the number's on the inside, and it's bigger than 1, this now becomes a horizontal compression. This means you're going to take all the x values from the parent function and multiply them by the reciprocal of the number that's inside the function. So you're going to take all those x values from the parent function and multiply them by the reciprocal of 2, which is 1/2. So 1/2 x, y values stay the same, and let's do it. You'll get -1, -1/2, 0, 1/2, and 1. And then y values stay the same, 2, 1, 0, 1, 2. Okay. I should do that in green, but you get it. All right. Okay. And now let's plot those. -1, 2, -1/2, and 1, which is right there. 0, 0, 1, 1/2, or 1/2, 1, and then 1, 2. And there is the horizontally compressed absolute value function. All right, not bad. So we've learned the majority of transformations, only 2 more to go. You now have shifts, stretches, and compressions. Yeehaw, right? Okay. The last type of transformation are reflections. All right. You get a reflection about the x-axis if the function is multiplied by -1, as you see there. So if it was y equals -2x, you would take x, the parent function, and flip it over the x-axis. That's it. So if there's a negative in front, that's all. Reflection about the y-axis. If there's a negative inside, you will flip it over the y-axis. So that would look like y equals the square root of -x. You would take that and flip it over the y-axis. So let's see how that works. Okay. So we're back on the parent function of the square root of x. We know how to graph that. And let's graph the other transformations. So up here, let's just say f of x equals the square root of x, which earlier we picked 0, 1, 4, 9, which we get 0, 1, 2, 3. And if I was to plot that below, 0, 0, not even close, 0, 0, 1, 1, 4, 2, 9, 3. Come on. There's the square root of x. Okay. And then the next is g of x equals the negative square root of x, which means that this negative means we will reflect over the x-axis. Which means if it's on the outside of the function, it only affects the y values, which means you're going to take the y values from the parent function and just multiply them by -1. X values stay the same. So x values stay the same, and all you do is take -1 and multiply all the parent function y values by -1. So 0, 1, 4, 9, and now 0, -1, -2, -3. All right, and plot that. Zero, 0, 1, -1, 4, -2, 9, -3. And there is the negative square root of x. All right, so you see we took the parent function, a square root of x, and just flipped it over the x-axis. That's it. Okay, and the last one here is h of x equals the negative square root of x. Okay, so the negative inside means we will reflect over the y-axis. Okay, so if you reflect over the y-axis, remember anything inside the function affects x values. So this means that all we're going to do is take the x values and multiply them by -1. That's it. So you'll get negative x, or -1 times x, and your y values will stay the same. All right, so from the parent function, we take these x values and multiply them by -1. 0, -1, -4, -9. And your y values are going to stay exactly the same. 0, 1, 2, 3. There you go. Now plot. 0, 0, -1, 1. Let me zoom in a bit. 0, 0, -1, 1, -4, 2, -9, 3. And there's the square root of -x. So now we have taken the parent function and flipped it over, or reflected it over, the y-axis. All right. those are all these transformations. So once again, we did shifts, we did stretches, we did compressions, and now we just did reflections, right? Look at all of these dance moves I have, right? It's perfect. Okay, so those are all the types of transformations. So if you know the parent function's values, then you will know how to shift the transformations. So it's important to know the original function's coordinates, so then you can apply the transformations to them. Makes it a lot faster to graph, trust me. All right, those are transformations. And now let's get into completing the square on a function. We've seen completing the square on an equation, but we've never seen completing the square on a function. So we're going to complete the square in the function, and then we're going to graph it using transformations. So let's try this out. And some of the same rules apply here. So remember, if you're going to complete the square, remember that the leading term always has to be 1. And if it's 1, we are good to go. The next step that we usually did was took this number and added it to the other side. Well, now we can't do that because this is in function notation. So everything has to stay on the right side. Everything must stay on the right side. So for now, this is the perfect form in function notation for completing the square. The form we're looking for is f of x equals x squared plus bx plus c. That's the perfect form for completing the square. And the leading term, its coefficient has to be 1. If it's in this form, we are ready to go. We are ready to complete the square. Which means what we're going to do first, we will, let's see. Well, I'm going to say group these two terms together because these are the two x terms we are completing the square on. So we're in the perfect form. So now we complete the square and we take half of -8 and square it. We'll get -4 squared, which gives me 16. Okay. Now on an equation, we would add these numbers to both sides. But now this is not an equation. This is a function. So on a function, the next step is to add and subtract this number on the same line. So what we're going to have is f of x equals x squared minus 8x plus 16 minus 16 plus 1. So we add it and subtract it on the same line. The next thing we're going to do is group the first 3 terms. Because remember, whenever you complete the square, these 3 terms become factorable. So we're going to factor. And over here, we are just going to simplify. All right, so this means you'll get f of x equals, and when you factor x squared minus 8x plus 16, that's going to factor to x minus 4 times x minus 4 minus 15. Okay, and then put it together, you'll get x minus 4 squared minus 15, and there it is. And you have now put this into a form that's called vertex form. But we'll worry about vertex form on the next section. Right now, we are graphing by transformations. So look at this function and think, what is the parent function? And if you said it right, the parent function is x squared. So the parent is x squared, which means we know what the graph of x squared looks like. And we had to graph this by transformation. So first off, let's put some parent function coordinates down. Let's put -2, -1, 0, 1, 2. That's it. That's all I want, which will give me 4, 1, 0, 1, 4. But now, let's transform it, which means we have to look at the above function and look at what transformations we are given. And we'll start with x first. This x minus 4 is a horizontal shift that is a horizontal shift to the right, which means you'll take all the x values from the parent function and add 4. So I'll have x plus 4 and then for my y values, well, let's look at that. This minus 15 is what type of transformation? This is a vertical shift down. This means that from your parent function, you're going to take all the y values from the parent function and subtract 15. So let's do it. We are transforming, so we'll start with x, add 4 to all these x values, and you'll get 2, 3, 4, 5, 6. Done with that. And now take all these y values and subtract 15 from them. 4 minus 15 is negative 11. 1 minus 15 is negative 14. 0 minus 15 is negative 15. 1 minus 15 is negative 14. And 4 minus 15 is negative 11. And we are ready to graph. There you go. All right, now let's graph. Here, I'll plot the parent function first. So 0, 0, oh. Are we not gonna make it to 15? We'll get it. All right, so let's make some stuff up. All right, so 0, 0, 1, 1, 1, 1, 2, 4, 3, 9. Oh, I didn't do 3, I just did 4, right? Okay. Okay, actually I can make my intervals different down below, so why not? So down here, we'll just go by, you go to 15, you can go by 2s, I think. Yeah. 2, 4, 6, 8, 10, 12, 14, 16. Negative, 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 negative. Okay, and now let's graph the transform function. And at 2, we're at negative 11, which is right there. At 3, we're at negative 14, which is right there. At 4, we're at negative 15, right in the middle. And then same points. So based on our transformation, we have shifted the original function to the right 4 units, and then we dropped it down 15 units, giving us this new graph. That's it. See, transformations a lot faster. All right, so there's our completing the square. Okay, now let's try it one more time. And this is the last one. Okay. All right. So we want to complete the square on this one to put it into that vertex form, to put it in the form where we see the actual transformations happening. So the first thing to do is this in the perfect form? And the answer is no. There's a 2 in front, so we have to get rid of that 2. But we're only going to factor it from these 2 terms. So I'll get f of x equals, and I'll take that 2 out, and that'll leave me with x squared minus 6x plus 19. I only factored the 2 out from those 2 terms. And now, on the inside, we have the perfect form. So we can now complete the square on the inside. And you'll take half of -6 and square it, which will give us -3 squared, which gives me 9. Okay, and now we must add it and subtract it on the same line. All right. Now this one's going to be a little tricky, so I'll show you. You're going to get 2 times x squared minus 6x plus 9 minus 9, all in the same parentheses, plus that 19 waiting outside. Ooh, yeah, right? What do we do now? Well, here's what we're going to do. We are going to factor this term still, and leave this -9 alone for now. Which means if I factor, I'll get f of x equals 2, and I'm going to put a bracket here for neatness. X squared minus 6x plus 9 factors to x minus 3 times x minus 3 minus the 9 that's there. I'll keep it in blue. Plus 19. All right. Now let's do a little more cleanup, and I'll get f of x equals 2. Keep that bracket there. Plus 19. Now, what I'm going to do to clean this up more now is take this 2 and distribute it to these 2 terms. Which means I'll get f of x equals 2 times x minus 3 squared minus 18 plus 19. And for one final cleanup, you'll get 2 times x minus 3 squared plus 1. And once again, you have the vertex form. All right, that one was tricky, right? But if you know what you are doing, you can honestly, what could I say? Well, you're missing a step, but you can actually go from this step straight to this step. But that's when you're expert level, okay? All right. Now let's look at our transformations. This too is a vertical stretch. This x minus 3 is a horizontal shift to the right. And then this one is a vertical shift up. Which means we know how to manipulate our parent function now. Because once again, the parent function is x squared. All right, so we have the parent function coordinates again. Now let's transform. We'll start with the x values. We have a horizontal shift to the right by 3 units, which means we'll take our x values and add 3. Now let's start with the y values. The first thing we have is a vertical stretch, which means we're going to take all the y values and multiply them by 2. But then we have a vertical shift, which means after we multiply the y values by 2, we have to add them by 1 because it's a vertical shift up. All right. Now, transform the parent function's coordinates. Start with the x values first. Add 3 to all of those. 1, 2, 3, 4, 5. Done. Now transform the y values. Multiply those by 2 and add 1. So 2 times 4 is 8, plus 1, you'll get 9. 2 times 1 is 2, plus 1, you'll get 3. And then 2 times 0 is 0. 0 plus 1 is 1. And then we should get 3, 9. Let's see. Yes. So 2 times 1 is 2, plus 1 is 3. Yep. Perfect. And now let's plot. Plot the parent function, 0, 0, 1, 1, 2, 4, 1, 1, 2, 4. Here's the parent function, and now plot the transform function. 1, 9, 2, 3, 3, 1, 4, 3, and 5, 9. So we took the orange function, the original function, we shifted it to the right 3, we stretched it by 2, and then we shifted it up 1 unit. Boom. So those are transformations and involving completing the square. Algebra, 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 algebra. Okay. So We definitely will touch more on completing the square on functions in the next section, but for now, this is transformations. So knowing the parent function and knowing how to transform the parent function, given your transformations, is very helpful. So know what transformations you are working with and know the parent function. And that's it. That is transformations. Done.